Well, good morning, and welcome to the latest installment of Mazzetti's Bending the Climate Curve Learning Series. I'm Christina Sanborn, Sustainability Practice Leader here at Mazzetti, where bending the climate curve is our mission. This morning, we'll discuss what it takes to decarbonize a campus by exploring Princeton University's journey. Princeton University is several years into a transition from a cogeneration-based district steam system to an electrified heat pump low-temperature hot water system. This is a keystone for its commitment for the campus to be carbon neutral by 2046, Princeton's 300th anniversary. All of the buildings on the district steam system will be transitioning from steam to low temperature hot water over the next 20 years as we build the system out. This webinar will discuss some of the ideas behind the project and the present lessons learned. Joining us today to share his story is Scott Sepsi, Director of Mechanical Engineering in the Facilities Operations Department at Princeton, a role he's had for 10 years. Prior to that, he was a member of the engineering team for another 28 years. And before that, he was a consulting engineer. At Princeton, he and his team are responsible for managing building systems in over 200 buildings on multiple campuses. Over the last several years, he's been focusing on implementing the campus transition to a decarbonized future while the campus is undergoing major expansions at the same time. He lives in Doylestown, Pennsylvania, is a registered PE in New Jersey and Pennsylvania, and is a lead AP. Today we're going to go over these particular learning objectives that you see on your screen. I won't read them out to you. You can see what they are. But I think this paints a really clear picture of what we're going to be talking about today. And today is, in fact, qualifying for one HSW CE credit. So make sure that if you, make sure that if you have not sent in your AIA number, when registering, please send it to info@mazzetti.com and we will get it taken care of. We will hold questions until after today's speakers have made their presentations, but you are encouraged to ask your questions at any time during the presentation via the Q&A function of the webinar. Today's session is being recorded. With that, Scott, take it away.
Okay, thank you, Christina. And I hope you're seeing my screen, right? Oh,
not yet.
Okay. There we go. How about that? Got it?
Yep.
Okay. So thanks for your introduction and for joining this webinar. And I hope you find some of this useful for your future projects. I'm going to talk about Princeton University's decarbonization program and the construction projects we are working on to minimize and eventually eliminate the use of campus steam on our buildings. This is a phased program that will last several years and address 10 million square feet of campus buildings. These are the learning objectives. We want to examine the reasons for converting buildings to low temperature hot water operation and the systems Princeton University is building to make this happen. Number two, learn the design and planning process for preparing buildings to operate at low temperature hot water. Three is learn items to consider in the construction and execution of a low temperature conversion project. Number four is learn about options available to replace steam process equipment. This is a picture of our cogeneration plant that's been here since the mid-90s. If you want to reduce your building's carbon footprint, you start by applying efficiency upgrades to minimize building energy use. And after you've done that, you can electrify the building thermal systems. If we want to bend the climate curve, we must stop burning stuff to heat our buildings. So the reasons to convert to low temperature hot water may come from within your organization, doing the right thing for core principles or appearances, but they may eventually come from without, maybe by higher carbon taxes. And converting a building from gas or oil-fired steam to hot water can be a phased process. It doesn't have to be all or none. In Princeton's case, reaching our goal of being carbon neutral by 2046, our 300th anniversary, will require a mix of projects. This is a picture of our new heat pump called the Tiger plant under construction. Building conversions and the heat pump plant are the largest part of this decarbonization plan. Our initial focus is on reducing Scope 1 emissions, what we burn on our campus for our district cogen system and chilled water system. Recently, we started really studying and producing a plan to reduce Scope 2 and 3 emissions. We are also relying on the grid serving our electrified buildings, and these are Scope 2 emissions, to get cleaner, and we are trying to manage that process too. We are in the PJM grid, which covers Mid-Atlantic and Northeast states. This grid has mid-level carbon emissions around an average of 625 pounds of carbon dioxide per megawatt hour. But New Jersey has made a commitment to clean up their emissions by 2035, so the emissions rates will drop. Now, you don't have to have a district thermal system to use some of these building conversion ideas to help reduce carbon emissions. For example, a building might have a gas-fired, high-temperature hot water building system that could be converted to a lower temperature localized heat pump system when the boilers age out. Whether you have a building-wide or a district-wide hot water system, it is hard to get heat pumps to run with any efficiency above 160 degrees Fahrenheit. And 120 degrees is a better target where COP's, coefficient of performance, can be 4 or higher. This is a picture from the Energy Information Association of grid carbon emissions, and this is where our grid on RFCE is 625 pounds per megawatt hour. Even though our cogen plant is usually cleaner than the grid, it will not get more efficient. Heat pumps that run off the grid multiply the useful megawatt hours per pound of emissions by the COP, which is around 4 on our yearly average, and the grid is getting cleaner. This is a picture of a typical, well, not typical, but a really bad steam line on our campus that we're removing and replacing a few years ago. Our cogeneration system, built in the 1990s, is aging out, and the steam system it's connected to has piping in some sections that are 100 years old. Our district chilled water system, built in the 70s, and though the distribution system there is fairly good shape, some of the chillers have steam turbines, or they're just 1970s vintage, so they're also in need of replacing. We would have needed major system upgrades even if we stayed on these old technologies, but we looked at the marginal cost of building a new district hot water system instead of rebuilding an old steam system, combined with our commitments to sustainability, and we decided to build a new state-of-the-art thermal system. And these are some of the issues with district steam. You have standby losses. You've got 300-degree products just sitting there waiting to be used. Insulation falls off, anchors fail, you lose condensate, you have traps to maintain, expansion joints, high standby losses, and so this is pretty easy to say goodbye to. And this is an overhead view of our new district hot water system being installed, one branch of 14-inch piping. A close-up of the building entrance for the hot water coming into one of the science buildings. On hot water distribution piping systems, you have to consider the hydraulics of the building. You have to do stress analysis, plan for future growth and robustness of the whole system, and you have to keep good track of what you've put in and how you're going to maintain it. The pressure and load profiles of your campus or building systems inform the material selections, the pipe sizing, and the routes. At the top of our campus, which have higher elevations and lower pressures, we may end up using plastic pipings, but we're not there yet. We use EN 253 steel piping at the plant and the lower parts of the campus, which we've already built. This piping is pre-insulated and only the weld joints are field insulated, which you can see on the slide. The piping is direct buried rather than building expensive steam tunnels, and the thermal expansion can be taken up by foam pads at strategic locations. We loop the system for redundancy of service, where you can have a branch out of service, but still feed buildings from another direction. We've added valves at strategic locations and added T's for system extensions of service. We've been careful about adding vents and drains at strategic locations. We inspect every weld and pressure test every pipe section. We're also careful about flushing, piping, and chemical passivation of the new piping system and monitoring water chemistry to avoid corrosion. And this piping system has built-in leak detection too, where we can pinpoint a leak. I understand that Brown University has reused some steam distribution piping for hot water, and we've done this inside of buildings where it makes sense. This is the new Tiger heat pump plant as it's finished. It has two CYK heat pumps that produce 1,700 tons of cooling each and 28 million BTUs per hour of heating. This system has 1 million gallon hot and chilled water storage tanks, which you can catch a glimpse of at the back of the slide here. We have a new standalone plant, this one tied to our existing cogeneration plant, gives us redundancy and resilience and allows easier conversion of equipment in our existing plant. When we get the heat pumps at the West plant, until we get those heat pumps running, we make the hot water there with a steam to hot water heat exchanger. This is a schematic of the Cub plant. This is a sister plant to the Tiger plant. It's across the lake from our main campus called the Meadows campus. It's similar, but much smaller in size. What you see here is the geothermal well in the green, and they're 600 feet plus in depth. And the plants over here with the heat pumps, you got hot water and chilled water storage tanks, and it's all the same water. It's just water that goes hot and cold, and the geo. We share the chemistry in those systems. We have about 1,000 geo-exchange wells now on the main campus and need to drill about 900 more as we build out the system. These wells are typically 600 to 800 feet deep. Some of the wells there have temperature sensors every 50 feet of depth to help monitor and operate the plant. We also have 3 small geo-exchange systems for clusters of graduate student housing and an arts complex. This is a picture of the heat pumps installed in the Tiger plant. Out of the plant, we distribute hot water between 120 to 160. The new system has low maintenance and low standby losses, very good insulation system. The heat pump coefficients vary, typically between 3 and 6. We try to balance the heating and cooling using the thermal storage tanks and the geo-exchange system. The storage tanks are for like daily or weekly use, and the geo-exchange is more of a seasonal battery. We have a common fluid for hot water, chilled water, and geo-exchange like the Cub plant. We reduce or eliminate cooling towers, and hopefully we can still get some IRA money. We'll see. We have return hot water temperatures in the low 100s. We talked about leak detection on the piping system. The Cub plant, this is different. It's a flat campus without elevation issues. So they're running at lower pressures, and they use high density polyethylene raised temperature piping. It's butt welded polyurethane insulation and HDPE outer jackets, which is cheaper than the EN253. Now, each building that we convert off of this plant results in a 65% reduction in CO2 consumed because of the cogeneration efficiency, which is not going to get any better, as I said, and the heat pump COP. And each building converted so far has resulted in roughly 28% reduction in operating cost. The shoulder seasons have the highest COPs where you can balance heating and cooling loads, and you don't have to use the field or the tanks. We have pressure control in the tanks that we need to drop the pressure into the tank because they can't handle the high pressure, and then we repump it back into the system. We use right now 50 to 80 million gallons of water per year in our cogeneration plant. The large majority of that is for cooling towers, and we expect the cooling towers will be rarely used in the future, and that's a huge water savings. We are working with accounting to try to get these IRA funds, as I've said, for the labor of installing this pipe. Now, how do we run the plant? We send out 43 degrees plus or minus chilled water, and we typically send out 140-degree water for heating. We can send out 160-degree water on the coldest days if we must, knowing that we can sacrifice COP for these few hours a year. And as buildings get more efficient, and as we find and correct local issues, we aspire to send out 125-degree heating water. So all our conversion designs are based on new heat exchangers inside the buildings that can produce 120-degree secondary water from 125-degree primary hot water. All the equipment inside the building then will work on 120-degree water. Now, instead of sending the heat into the sky through our cooling towers, we reject the heat into the ground and store it for use in the winter. For short-term imbalances between heating and cooling, we use our thermal storage tanks. Over the course of a year, we charge our geo-exchange fields with rejected heat during the summer, pull that heat out in the winter. And during the shoulder seasons, as I mentioned, where it's the COPs can get up to 6. This is another photo of the finished Tiger plant showing skids with the pumps for the geo-exchange blue. The green is the cooling kit, and the orange is the hot water kit. This is a map of the campus showing the new hot water piping network. The Tiger plant on the far right and the cogen plant over here on the bottom left are now tied together by the black lines. The black lines are already installed, and that was the first thing we had to do, was connect these plants so they could back each other up. And we've built out the engineering quad and built out into the central campus for dormitories. And the colored buildings and lines, piping lines, are yet to be built. As we continue to build new buildings, we are also converting existing buildings from steam to hot water. We'll continue to expand the hot water network, convert buildings, and cut branches off the steam system over the next 15 to 20 years. The colored branches of buildings are yet to be built. And at this point, we've converted 14 buildings and brought four new buildings online to our new district hot water system. We've converted dormitories, academic, athletic, administration, and science buildings. We will have to add heat pumps to match the increasing demand from the buildings as we build this out. Note that there are loops in the system so we can feed from multiple directions, and we've been strategic about isolation valves where we can do repairs or additions for future branches. So planning, the second objective, planning, preparing, and designing for converting buildings to low temperature hot water. The starting point there is getting a good handle on where and how much steam is used in the building you're studying. Having an accurate schematic of existing steam, condensate, and hot water systems will be essential. Steam might be used for ventilation or makeup air preheat coils, reheat coils, humidification, domestic or lab hot water systems, process loads, perimeter heating with convectors, fan coils, unit heaters, cabinet heaters, valence units, radiant heating systems. And you have to decide if you're going to do a full or partial conversion. When building conversions can be done as an alternative to replacing steam equipment, this makes the most of your investment. If you replace functional, good heating equipment early, you're losing its remaining value. And this is where partial conversions can come into play. For example, if you are going to convert a building in 5 years, but you need a new air handling unit now, you want to make it run on low temperature hot water now and let the building systems catch up later. Even if you're using a higher temperature hot water system now, size the coil so it can operate at the future lower temperature. The coil sized for lower temperature but running on higher temperature temporarily may need a control valve change, but it's just as likely that it will work in a different segment of the control valve's normal operating range. Or you may decide on a partial conversion because you don't have a solution to cutting off process steam, which is the case for us in some of the science buildings. In our biology buildings, we did partial conversions because we still need steam for cage washing, autoclaves, and other processes. However, converting the mechanical equipment, including preheat coils and domestic and lab hot water heaters, reduced the campus steam demand and carbon significantly. And it gave us load for our new heat pumps, which don't have great turndown ability. If you think about the metric of dollars per pound of CO2 eliminated, laboratory preheat coils are the best bang for the buck. The building primary hot water system and service was sized to support the future solutions to the process equipment changes. Those future solutions may include more electrification within the buildings. And so you have to evaluate spare electrical capacity too. After determining which equipment has aged out and needs replacement and whether you need to keep some steam for processes, you need to evaluate the viability of the remaining heating equipment. And this is a picture of one of the science buildings in the middle of a conversion. You can see the original steam main coming into the shell and tube heat exchangers. The new plate and frame heat exchangers are in place, and we're going to demo the white pipe, the white heat exchanger in the near future. And the next, so also more factors to consider. Can you reduce the demand through maintenance and energy projects? Can you use low flow fume hoods, upgrade vivarium controls? Even simple things like door or window upgrades or seal improvements that can reduce parasitic infiltration loads can be useful. Phasing is something to consider closely. Phasing, as we think of it, includes installing the new system, testing it as far as possible, and then when you're confident it is ready, remove the original equipment. For example, here are two domestic water plate and frame heat exchangers. The second one replaced the original unit after the first unit was installed and tested. Phasing pump installations also follows the scheme. Air units are converted 1 or 2 at a time, perhaps over a weekend shutdown. Perhaps controls need temporary services to test and commission new equipment. Add valves that can phase and sectionalize your hot water network. Perhaps the perimeter system is the first to run on low temperature hot water and the reheats may be flipped later. You may need temporary systems as part of a phasing to keep your equipment in operation. The contractors and the construction managers should know as much about phasing as possible to accurately plan and price their work. Reusing steam piping for hot water, either supply or return, might help with phasing and save money. Condensate lines will be likely too small to reuse, but the steam piping could be reused. You have to do a risk analysis. Do you want to replace, for instance, vivarium reheats now in a limited construction window, or do you want to wait for a future renovation project, perhaps when the vivarium needs equipment upgrades. Don't bite off more than you can chew. Satellite plants. We sometimes build a kit like we just saw in the previous slide to do multiple buildings. Groups of maybe 2 or 3 that are then sub-metered, but they're close enough to run secondary piping, which can be plastic, to feed those systems. So you save all kinds of money on heat exchangers and controls for the primary production kit. You have to consider, well, utilities planning for a district system. Consider building one low temperature hot water production plant that can serve multiple buildings. That's the satellite plant if they're close by. We've done this on multiple sites and saved on secondary distribution piping costs, and which are the lower temperature and pressures, and lets us get off of the EN 253 steel piping. We use polyethylene piping between buildings. It's a fraction of the cost. Savings includes space and equipment and controls and piping. Ideally, the district hot water system arrives at the building just in time. And if it doesn't, you stay on your parallel system. That's another thing about risk and phasing. Or you'd have to rent a hot water boiler, and we've had to do both. Understand as much as you can about the potential future plans of the building and optimize the path for new utilities into the building. Utilities planning also should include removing old steam and condensate piping systems and their parasitic losses. Another important factor is setback testing in your design process. This is a picture of 15 control valves on reheat coils over the course of a couple of hours that we, on a stressful day, design type day, and we looked and found the ones in red, and this is using a heat map. The valves in the red were already at like 10 volts or near 10 volts. So that means with 180 degree or 160 degree water going to the coils, they were already maxing out their operation. So we had to study these valves closer and the coils and see if we could use them or whether they needed to be replaced. So you look at the historical data for the equipment and see its response to heating with higher temperature hot water. And I want to say that the blue boxes were a low voltage, so the valves were not open fully, so they look pretty good. Here we found that many of the control valves, wouldn't work, so they're struggling and at 10 volts, and it's probable that they need replacement. But one thing is we had to go out and make sure that the valves were actually fully open, even though they had 10 volts. The coil, if the valves were sticky, and we've had this problem, the valves might not have been fully open. So it could have been a control valve problem. And so check this before you condemn the coil and valve to be replaced. So this is a trend of a particular coil over a longer stretch of time here. The red is the voltage to the valve, and you can see here at 10 volts, the set point, which is green, was not made. The light blue was the actual discharge temperature, and it couldn't make when this is the supplier, and the lower or the darker blue is the incoming air temperature to the coil. So even at 10 volts, it couldn't make the set point. What you really want to see here is an orange line that's below 10 volts, and you want to see the light blue line over the green line all the time. And that means it's working correctly. So for equipment that seems to be operating at 180, we used our building automation system here, or data loggers, to trend the response to selected areas while supplying lower water temperatures. You set the supply water temperatures back slowly and see what happens. Hopefully, you will find that the terminal equipment can still meet the demands with cooler water. This test will reveal which units need a design for replacement or upgrade. Trending should be done in cold weather for perimeter systems, but it is not absolutely necessary to test at the design temperatures, as the response at design conditions could be extrapolated. Our winter design temperature, which is the outside air temperature of 10 degrees Fahrenheit, we find that testing the perimeter heating equipment at 20 or 25 seems adequate. The distribution piping in the building should probably be okay, even if you have to replace terminal equipment. You run it at lower temperatures, but you need to check the velocities and try to design for similar delta T's between supply and return, so the flow rate doesn't have to change much. Items that you might want to test include all these heating elements: reheats, fan coils, cabinet heaters, fin tube convectors, induction units, valence units, etc. For interior reheats, not affected by outside conditions, testing can happen at any time, and a few days of normal occupied or unoccupied conditions should give enough data. When labs need deep dehumidification, as is this slide shows, which may be in a summer or shoulder season, and internal loads are light, the reheat coils will see their toughest duty. Hot water preheat coils or boosted glycol preheat coils should also be studied and tested. Capacity analysis could also be done looking at product data and submittals to cross-check. So our setback testing process enumerated here is: use the BAS and data loggers if you have to. Notify the users and interested parties that you're going to do a test in case the temperatures get out of range and the alarm doesn't go that it's a problem. Trend representative or challenging spaces like corner offices. Override setback temperatures if needed to represent occupied conditions. Set up alarms to stop a test as needed if it's in a critical space. And 3 or 4 cold days should suffice. Reset the supply water temperatures slowly so you can see the response. Trend outside air versus space temperatures and valve position for perimeter spaces or interior, really. Trends supply water temperatures and space temperatures, actual versus set point, and the valve positions for interior spaces. This testing process is also useful as a standalone retro commissioning exercise, even if you don't proceed with a conversion. You can identify problems you have or weak elements in your system. After setback testing, what do you do with this information? Firstly, we've been finding that a lot of equipment, when designed for a 180 degrees or 160 degrees, will still work well with 120 degree entering water. This is a bit surprising. Can partially be explained by the probability that envelopes and equipment work better than predicted by models, and by the conservative nature of system design. A paper I just saw from SIBC Journal, this in England, found that most typical houses there will be able to switch to lower temperature heat pumps from their gas or oil boilers without major equipment modifications. It's rather in line with what we've seen at Princeton. We've had good success retaining valence units and reheat coils in particular that were nominally selected at 160 or 180. So design then what you need to replace along with the other project inputs. Can you combine your project with maintenance projects? If you need to replace a coil in an air handler that's 30 years old, then you probably want to replace the entire air unit. You may plan partial or phased building conversions with the maintenance as the driving project. You can build out low temperature hot water equipment over time while you continue to use a steam-based high temperature water system, maybe 160 or 180. The last piece of the system then might be the arrival of central hot water piping or the installation of new low temperature heat pump within the building. You may also want to upgrade your controls. You may need to add sensors and programming to aid in control and commissioning of new systems. And as an example of this, we added thermostats in a dorm room that we had done setback testing on, where we previously had only run the building system with single sensors for different exposures of facades. There was really no feedback into the BAS system for individual rooms. Now the upgraded system will quickly respond to problems at specific locations and alert us to problems on a room by room rather than exposure level. The final product is better comfort for the occupants and better diagnosis for future maintenance problems. Design building systems in parallel where you can. For occupied buildings, if there's room to build in parallel, a new hot water system being installed with the existing steam still active, as you saw on that one slide a few back, then you can minimize the shutdown windows and perhaps retreat if something goes sideways in your project, like a busted schedule. In my experience, this is really an essential part for occupied buildings. Again, it's not all or nothing. Key areas might be paralleled with other systems offline longer for demo, then build sequence. When the building is commissioned and running on hot water, then you can demo the steam equipment and recover the space that was used by the steam equipment. We're finding that many of our converted mechanical rooms have lots of floor space and seem empty, actually, sometimes. Obviously, parallel systems are not necessary if a building is offline, for example, a dormitory that's unoccupied for the entire summer. You have to work with building tenants and neighbors that will be affected by upcoming projects during the programming phase. For science buildings, tenants care about noise, vibration, shutdowns, disruptions to temperature and humidity, and you need to be transparent about the changes in space usage. Perhaps access to certain items will be temporarily or permanently compromised. You may need temporary systems to maintain continuity of services for science research. You have to work out programming issues, layouts of equipment, and the space requirements. Don't just assume like an empty storage room could be used for new parallel equipment installations. We learned this the hard way when we had to redesign a project. We assumed a room was available to us, and actually they wanted it for future research. So the layouts and logistics must be, and they must work within the construction window. You have to design for redundancy and resilience, designing for N+1 where you can on critical buildings, and study possible failure scenarios. Consider installing, for instance, 2 heat exchangers, maybe at 80% capacity rather than at one at 100%. Consider 2 hot water pumps with at least 1 hot water distribution pump on, and all freeze pumps on standby power if you have it. So you can, for the power failure, can still heat the building's perimeter at least. Pumps should be fed out of different control panels. If you lose a panel, you could still have a pump running. Critical control panels should have standby power or UPS backup. As a backup plan for equipment to be retained, you can design proof of concept. If you have any hesitation about reusing a large tranche of existing equipment, you could design a replacement of a small subset of these units rather than replace everything and break your budget while doing this. In the first dormitory we converted, we have 200 valence units that seem to work from the setback testing, but we didn't test every unit. The units were 10 years old and in decent shape. We decided to replace 8 units in the dorm rooms on corners of the building that were most difficult to heat. We also installed a controls upgrade, as I described before, that lets us trend every room, and we trend these rooms during the first winter. So for the first winter, our backup plans for cold complaints would add space heaters, minimize setback, boost flow of air and or water temperatures or flow, raising ventilation unit supply temperatures to supplement the valence units. installing these new units during the conversion let us learn the details and difficulty of replacing the units and gave us a full pricing preview and micro lessons learned in case we needed to have a major replacement project the next summer. And we found that we're replacing only 2 more of the units this summer. So this is what I mean by a proof of concept. We've never used a design build process before these on the campus before these conversions, but now we're doing that. We're building these conversions in phases, groups of 3 or 4 buildings at a time. So we hire a design engineer to produce schematic design documents, which we use then to bridge over to a competitively selected construction management team to finish the design. And this includes the final design engineer, and in some cases, the engineer remained on the same team throughout the project, but not always. The CM also hired a mechanical contractor at an hourly rate to advise the project during design, and this is the critical and best part of it. We had then on the construction team someone who could help us work out logistics, alternatives to pipe routing, and someone that knows exactly how long it'll take to build parts of the system, which informs the phasing process. So the construction manager at the end of this design, finally, we take competitive bids for the subcontractor to develop a GMP. The great advantage of this is optimizing routes and getting the planning done early. So this is a schematic of the final design of a system in one of our science buildings. And here the orange line is the primary district hot water system comes in. It always goes to heat exchangers where we intercept and divide the building systems from the district system for chemistry and pressure reasons. But here in the basement, they go to domestic and lab water heat exchangers. Upstairs, they go to hot water systems for reheats and a boosted glycol heat recovery system where we try to pull heat out of the exhaust air and add a little more heat as we need through a heat exchanger into the glycol. So really, there's 4 different hot water systems here in this building, in this science building. We monitor, we have flow meters at the building entrance, differential pressures that inform the plant of what's going on with the district system. And that's typical for every building. So the third learning objective is actually executing the project, building it, things to consider. For work inside of occupied buildings, you want a good team that knows how you work and what you expect. You need good project management and people that are available to troubleshoot issues during burn-in when systems are getting tuned and occupants may be inconvenienced or uncomfortable. You may need controls contractors, pipe fitters, and construction managers on a Zoom call on a very short notice. Having on-site maintenance personnel is also a great advantage. Good project managers and site superintendents who are always available. You want good logistics planning, anticipation of needs, tech support from the owner who can work up alternatives, understand risks during transitions, good schedulers and contractors who knew how long work will take. And you keep the occupants involved with the big picture and shutdown schedules. Having the right people at the table from the building at the occupant side is important. Shutdowns, you have to coordinate with the building occupants. There'll likely be many shutdowns of electrical and control panels to add or change pumps or air units to replace coils. So you have to find a schedule everybody can live with. Shutdowns can be combined with maintenance testing and can be very useful. While you're replacing a preheat coil, install new humidifiers or work on electrical panels, change filters, replace lighting, verify sensors are working, install control program updates, clean airflow stations. There will also be work and traffic in hallways and occupied rooms, and these disruptions have to be socialized early in the project. Hold contingencies of money for off-hour work to address these issues. And if you're changing outside utilities, you'll need good communications with a host of other interested parties like neighbors, public safety, parking, and transportation. Risk. Even though you looked at risk during design, take another look. If shutdowns are going to take too long, you may need temporary systems. Or do you really have N+1? Does your backup pump really work? Get equipment's lead times are important. Release equipment that you need early, get good submittal reviews, and schedule startup technicians early and get their commitments. The easiest transition is just flipping a valve. So set it up for that future scenario if you can. Try to put freeze pumps and distribution pumps on standby power, as I've said. Failure modes, you have to think of what happens. Schedule the time of year. That's a risk too. You want everything in place and tested before the seasons or the building demand changes. For us, most buildings need to be ready for winter by mid-October. For dormitories, it's late August when domestic water availability is critical. And if you can't finish it based on the schedule, then you're going to have to face the work differently. You should scrub existing systems before you start. Make sure that the hot water piping risers are clean, blow down drains, clean strainers, make sure valves and control valves open and close. If you don't do this, your project will be blamed and it'll extend your project and while you make corrections. Scrub controls for issues before the conversion. Things like building pressurization problems or simultaneous heating and cooling can be magnified when using lower temperature hot water. Take pre-demo snapshots of systems or subsystems that were not touched during the conversion so you can reinstall them to their starting conditions. The spot check flows and duct pressures before you cut those systems open. For example, deeper hot water coils with more rows might have higher pressure drops, and you might need to rebalance airflows, speed up fans to get the same CFMs. New controls, this is a typical Gantt chart, but near the end of the project, make sure your controls are in place and ready to help you with trending so you can monitor the systems closely from day one. Your controls engineers, controls contractors, and tenants have to be on the same page for what they really need. And there's no reason that controls graphics or flow meters, which can help diagnose projects, can't be in place well before systems come online. And if you're getting new types of equipment like adiabatic humidifiers or equipment with new onboard controls like new brands of domestic water heaters, you have to engage early, getting design and submittal reviews to make these transitions smooth and timely. Review the installations, do it early in the commissioning process on site. Closely review the location of sensors such as differential pressure or coil temperature sensors installed correctly and you got the right coverage. We've had to replace sensors that did not cover coils adequately, so that's a lesson learned. You may have to adjust or eliminate setback because with lower delta T's or lower temperatures in the system, spaces may not be able to ramp back up as quickly as possible. So you may have to eliminate or, again, modify the setback schedules to give you more time. Provide adequate training of the new equipment, read-throughs of O&Ms before their training comes. Schedule and videotape the training. And if you don't have staff on site able to monitor equipment, you should at least have someone reviewing the BAS trends and looking for anomalies. And consider supply chains for new equipment. How long will it take to get a pump if it fails? You may want to stock stuff even before your warranty runs out. So you're going to be challenged by projects that wind down by unintentional software bugs, that new programs that overlay old programs, and the new products and types of equipment. and deciding where to draw the line between the BAS and the onboard controls. So objective number 4 is talking about process steam loads, alternatives to district systems. If you want to get completely off steam, you got to understand and deal with process loads. These include autoclaves, cage washers, tunnel washers, sterilizers, and humidification. Examine the process. Is it right sized? For example, can wash down of cage be done at a lower temperature, pre-wash down? We did this and changed a process in one of our science buildings. Steam generation could be done instead of a district system. It could be integral to the equipment. You could have local generation for multiple devices in adjacent buildings. Building power has to be studied, though, if you try to electrify the process. If you have a satellite plant for just a cluster of buildings compared to district heating, the demand might get too large and you may require a boiler operator. Steam system heat pumps are under development and some are near commercialization. This slide shows a mock-up of a steam generating heat pump. Some companies working on this include Atmos Zero, Cobelco, and JCI. Development of funding in the US has been in part through NREL, and these heat pumps are approaching temperatures and pressures needed for autoclaves. I will mention that high temperature hot water heat pumps are becoming available also, and you could use these as a direct replacement without modifying 180-degree terminal equipment. Vaporized hydrogen peroxide might be an alternative to steam sterilization. Probably not, but it's worth asking. And then there's adiabatic humidification. But first, the cage washers here. On the left, this is a cage washer. On the right, an autoclave. And again, you could buy onboard steam generation for autoclaves and perhaps modify cage washer operations. They have intermittent and dynamic steam demands, but the heating requirements could be reduced by lowering the temperatures and could be eliminated completely by electrically boosted high temperature hot water. Maybe you preheat with a heat pump and finish it off with an electric resistance heat. What they really need is 180-degree plus water for the sterilization. Adiabatic humidification, I'm calling this a process. It's a different process than isothermal humidification, which we use. First of all, make sure that you understand the needs for the humidification, because reducing the load can save you money on the size of the kit and operating of money too. We've used direct steam injection isothermal humidification up until now, but if there's space in an air handler, and if you're not using steam in the building for other processes, then we're likely, to switch to adiabatic humidification. We're still on a learning curve with these systems, and there seem to be 3 major vendors, and we've used all 3 on the campus and are tracking their performance. These humidifiers require a reverse osmosis water, which can be produced on a central humidifier skid shown here, and distributed to various air handling units with local controllers. Control sequences on air handlers need to change because the air must be heated by the preheat coil higher than normal to around perhaps 80. This varies with load and entering conditions compared with our normal like 50, 55-degree air. And then with the adiabatic humidification, the preheated air is recooled as it passes over the grid of the RO spray nozzles shown on the left, which absorb the water into the airstream and cool the airstream. So you end up with the same process leaving the air handler. But absorption distances may be longer with these adiabatic systems, so you gotta have room in the air unit. The absorption pads, which show here on the left, absorb the droplets and give the air another chance to reabsorb the water off the pads. Now they're more the grid with the humidifiers are run by solenoids, and they're just operated in different steps. with nozzles. The drain pans and walls of the air unit should be stainless steel because it's aggressive water. Absorption efficiencies are not as good as with isothermal humidification, and there's also reject water during the production of the RO water, but you might be able to recover that water into a gray system. And the maintenance of this skid requires attention. And this is another picture of the grid and the nozzles. And that's it. I might do run out of time. Okay.
Thank you so much, Scott. That was fascinating, and you had so much good advice for our audience. We have a couple of quick questions in the, we have one very quick question in the chat. Are the York CYK machines used in the tire plant 6-pipe machines or 4-pipe machines?
4-pipe.
4-pipe.
Yeah.
See, that was an easy one. And then we also had a question, can we review the parameters on the slide to check existing zone performance at reduced hot water systems temperature? Hot water supply temperature?
Can you review it? I mean, go back to the slide?
Yeah, I think they want you to go back to the slide and maybe explain the parameters.
Maybe it's this one. Wait, this one here? Is that the one? I think this is the one. I mean, this is so a trend. It could be, you know, anything. You look over the time that you've got the trend available over a cold day, and you look at valve position and the set point you're trying to reach. And here, what you see is the valve was fully open, but it wasn't meeting set point because it had to lift the temperature of the supply air coming into the coil, right, from 44 up to 65, and it couldn't do it. So we need a bigger coil here. So this one is a fail. I think that's the slide you wanted, right?
Thank you. I think it's time for us to wrap it up. If you would take down your slides, I'll share the remaining slides.
Okay.
So thank you all for joining us today. We appreciate your time, Scott, and I learned a ton. So I hope all of our attendees did as well. And thank you for the questions that you submitted. I'm sorry we couldn't get to everything that you had questions about, but I'm sure that we can arrange for answers if you want to contact us at info@mazzetti.com. Next month, please mark your calendars for the Bending the Climate Curve Learning event on the 15th of April at 8 a.m. Pacific, 11 Eastern. Our speaker will be Dr. Anne-Christine Dolame, looking at the climate crisis from a perspective of how the human brain makes decisions based on evolutionary influences on its design. This talk will provide listeners with a different lens to help frame the challenge in new ways that can help change behavior in pro-environmental directions. How this can apply to healthcare sustainability in the clinics and research laboratories, global priorities and policy, and what we can do to shift paradigms towards both short-term goals and long-term thinking will be the focus of our next exploration. Thank you all for joining us today, and we'll see you next month.